This talk is about the discovery of new materials. Typically, when new materials make the news, it is about how they improve our lives, such as with better batteries or more efficient lighting. In these cases, materials discovery is driven by technological progress. We want our batteries to be smaller and our electric lighting to be more efficient. This is the materials pyramid, and it provides a good overview of materials research. The base of the pyramid represents the huge number of materials that are known to exist, but very little is known about their properties. The top of the pyramid represents the small number of materials that are useful and have been studied in detail. New materials enter at the bottom and sometimes work their way up. But there is a hidden side to materials discovery that you almost never hear about. And this is about the ability of certain materials to organize and drive scientific progress. High-temperature superconductors are a good example. These materials have been studied for more than 30 years, but we still don't understand them very well. The reason new materials can surprise us is due to a phenomenon called emergence, or emergent behavior. In a famous article in Science called More is Different, P.W. Anderson pointed out that at each new level of complexity, entirely new properties appear that cannot be predicted from first principles. Once you start thinking about emergent behavior, you will see it everywhere. Human societies, language, and insects all show emergent behavior. The flocking behavior of birds arises from interactions between individual birds. Likewise, superconductivity arises from interactions between electrons. Scientific progress requires a constant supply of new materials to challenge our understanding. This figure illustrates the enormous gulf between complex materials we make in the lab, such as high-temperature superconductors, and naturally complex matter, such as even simple forms of life. There is plenty of room for future discoveries. So how do we go about finding new materials that challenge our understanding of matter? The periodic table is a big place, and there are literally millions of possibilities. Do we start by mixing elements together randomly? How do we proceed? Is it just a fishing expedition? Do we need to rely on serendipity? Fortunately, no. Although serendipity is always welcome. The path forward is similar to the way mathematicians solve math problems. They use heuristics. These are general rules that help one make progress. It turns out that there are many heuristics we can use to try to build complexity into matter. One example involves a heuristic called frustration. Frustration refers to the inability of a system to satisfy all the conflicting demands and interactions. One puts the system in an uncomfortable position, and often the system will do something interesting and unexpected to remove the frustration. In philosophy, this concept of frustration is known as Buridan's ass and is named after the French philosopher Jean Buridan. In the Buridan's ass scenario, a perfectly rational ass will starve to death if placed between two equally good haystacks, as there is no rational reason to pick one over the other. In materials, the simplest illustration of frustration is known as geometrical frustration. Imagine that at each vertex we place a magnet, and we want neighboring magnets to point in opposite directions. For a square, there is no problem, but for a triangle, it is impossible to satisfy all the interactions. What will the material do? Over the years, these ideas about frustration have led to a lot of theorizing about a new state of matter called a quantum spin liquid. The idea is that quantum fluctuations prevent magnetic order down to absolute zero, but even though there is no order, new properties emerge. In 2006, a theorist at Caltech named Alexei Kitaev created a mathematical toy model of a quantum spin liquid. What is nice about Kitaev's model is that it is exactly solvable. Unlike many other toy models, this model has a clear solution that everyone agrees on, and it makes clear predictions about what should be observed. In the Kitaev model, the magnetic moments sit on the vertices of hexagons that form a honeycomb structure. The frustration is built into the model because each of a moment's neighbors wants it to point in a different direction. The moment ends up fluctuating wildly because it is not happy no matter which way it points. The strong fluctuations organize themselves into emergent excitations called quasiparticles. You can think of these quasiparticles as something like a pattern formed by flocking birds. These quasiparticles are known as Majorana fermions. and they come in two forms. One is highly mobile, and one moves very slowly. Majorana fermions are named after a brilliant Italian physicist named Ettore Majorana. In 1938, Majorana stepped onto a boat and vanished. No one knows what happened to him. Majorana fermions are fermions that are their own antiparticles, and therefore they have no charge. At this point, we have a toy model, but nothing to do in the lab. In 2009, that all changed when Jekeli and Kalulin argued that the Kitaev model might be realized in certain real materials. They even provided some great heuristics. Experimental groups from all over the world tried to find Kitaev quantum spin liquids. At first, most of the effort was spent on materials containing iridium, but the results were disappointing. In 2013, a group of us at UTK and ORNL started working on a material called ruthenium trichloride, RuCl3, which seemed to have all the right ingredients. It took a few years, but eventually ruthenium trichloride became recognized as the best physical realization of a Kitaev quantum spin liquid. The crucial evidence was provided by very detailed comparisons between theory and neutron scattering data. Observing the media response to our work was amusing. One of our collaborators was from the University of Cambridge, and their media team put out a rather extravagant press release. The story then went a bit viral in the scientific press, and eventually we made number 18 in Discover Magazine's Top 100 Breakthrough list for 2016. Ruthenium trichloride is a good example of how new materials drive science. Thank you.